How's it going? We got another quick video for you guys today. We're going to be looking at large language models and how they're being used in robotics. So there's a bunch of different papers coming out of these research groups, but largely it's mostly the same idea, which is that robotics is using large language models as part of their systems in order to get much better performance. Right? So robotics is a field which I have a bunch of kind of expertise in, and I've done a bunch of work there. But it's kind of the problem with robotics is that you're creating a chain out of different technologies, such as your hardware, your vision sensors, your vision algorithms, your control algorithms, and so on. And each of those individual little links within this larger chain that you need to create when you're trying to do something in robotics, you're kind of limited in your performance by the weakest part of that link. And large language models have emerged as a potential solution to some of the problems that we were running into when you were trying to use robotics in the real world. And yeah, let's go ahead and see what happens here. So Everyday Robots is a group within Google Research. I think they actually closed down relatively recently, which means maybe this video is a little bit too late. But Everyday Robots worked on these robots that they had inside Google, which are basically like a Roomba, and then with a big tower on top of it. And then they have this little part here, which is basically a little depth sensor, kind of like you would see on the top of an autonomous vehicle. The little Velodyne sensor, it's like this spinning laser that shoots out little lasers and can tell you the depth. Except here, rather than it being sitting on top of the vehicle, it's now like this, and it sits underneath the chin of the robot. The robot also has this head, which has a pan tilt, and then it also has a twist, which means that the robot can choose what to look at. And then you have this, a single arm for the robot, right? So it has 1 degree of freedom here, 1 degree of freedom here, 1 degree of freedom here, another one here, 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 and so on. And then it has a little gripper, little pincer gripper. So unfortunately, I think this division was kind of not shut down, but largely defunded. I think some of the people that work on this are still there. Chelsea Finn, Carol Hausman, these are pretty awesome people that I've gotten the chance to work with, and I definitely will continue to check out their work as they continue to push out stuff like this. Okay. So Google's research state-of-the-art language model, PaLM. So Google has their own language model. So OpenAI and Microsoft have GPT. Meta and Facebook have Llama, and then Google has PaLM, right? Introducing PaLM Saycan, a robotics algorithm that combines the understanding of language models, right? So language models can pretty much take any blurb of text and do all kinds of different things with it, right? Either what they were originally trained to do is take a blurb of text and then continue to basically add to that blurb of text token by token or word by word. But they can also be used to kind of understand what is in that text, right? And that's what they're going to be using these large language models for in this particular application, with the real-world capabilities of a helper robot. So capabilities, maybe a little bit loose there. These robots aren't in everybody's homes, right? They're just doing very constrained tasks inside research groups. So PaLM Saycan works. How a PaLM-enabled helper robot bot performing a series of complex tasks using chain-of-thought prompting and the step-by-step solution needed to carry out these requests. So chain-of-thought prompting is something that falls within the field of kind of prompt engineering, which is a relatively new field, but it's this idea that you can kind of engineer your prompt in such a way that the model, or that the large language model can produce a output that has specific properties. So one example to understand what chain-of-thought prompting is adding the word "let's think step by step" to the end of your prompt, and that forces the large language model to kind of show its work and basically provide a set of steps that perform the task that you want to and you describe in your prompt. And by doing that, you actually get a fundamentally different answer from the large language model than if you hadn't included that, like, let's think step by step, right? So chain of thought prompting, very useful technique. So we have here, select a task for the helper robot, see how Palm Saycan interprets that task, see how the helper robot executes the task, and then learn the step-by-step solution behind Palm Saycan. Okay. So 1, the task. I just worked out. Can you bring me a drink and a snack to recover? Robots struggle to understand complex instructions that require reasoning. By using an advanced language model, Palm Saycan splits the prompt into subtasks for the helper robot to execute one by one. So this is basically the key part, right? Is that until large language models came out, you had to basically program a robot to do anything. You had to very explicitly describe the robot, like down to like the exact trajectories and positions, right? You couldn't just say, hey, grab this cup. You'd have to say, move your hand to this exact position, then grip it until this exact force is felt, then lift it in this exact trajectory, right? And all of that had to be described in code. And that meant that it was basically impossible for anybody that wasn't a robotics engineer to use robots effectively. And that once a robotics engineer created a robot in a particular factory to do one specific task, that was basically it. And if you ever wanted that robot to do something different, you'd have to hire a robotics engineer again, and they'd have to spend a bunch of time to make it do a different task. So robots for the past 30, 40 years have been basically very, very limited and constrained into very specific jobs that they do over and over and over again. And if anything is different in those jobs, anything changes, it basically doesn't work anymore because the instructions that they follow are very precise, right? So large language models have changed that because now large language models basically have that fuzziness that you want, right? And you can describe a task in natural language, which is just the language that we speak every day, right? Like, I just worked out. Can you bring me a drink and a snack? And then this large language model, Palm Saycan, will split that via chain of thought reasoning into a set of instructions that can then be executed by the robot. And those instructions are going to be more precise, and they're going to be what the robot actually needs. So it's this large language models are helping in robotics in the problem of taking high-level instructions being given by a non-robotics engineer, a non-robotics expert, and how do we turn that into a set of instructions that the robot can actually execute? Can you bring me a drink and a snack? This is the robot talking to itself. The user has asked for a drink and a snack. I will bring a water bottle and an apple. Which uses chain of thought prompting, which interprets the instructions in order to score the likelihood that an individual skill makes progress towards completing the high-level request. So the robot itself, well, it's not the robot. It's the large language model that has been told that it is the robot, right? So it's all kind of weirdness with what that means for consciousness, but the large language model that is interpreting this is scoring the likelihood that an individual skill makes progress towards completing the high-level request. So it can evaluate whether or not each of the steps that it'll create allow it to get closer to the actual high-level command that the human gave it. So we see here, we see this little robot. It's wandering, wandering, wandering. You can see its head. It's looking for the tables and stuff. You see this little LiDAR sensor spinning. This is how it sees, right? Got the red e-stop button in case you ever need to shut off the robot because it's attacking someone. You can slam that red button. You can see how the robot went. It grabbed that bottle, and now it go ahead and very slowly moves to this table and then puts that bottle down. There you go. Here you go, same thing. Open, all this stuff here, this is all pre-scripted. So up until the robot basically gets to that position, that's probably all hard-coded. And then once it goes into this position, that is where it's actually kind of using its intelligence to actually do a little bit of servoing is one way to describe it. Visual servoing, where it's kind of adjusting the position of its hand such that it overlaps into the object and grabs it. This is probably all hard-coded here as well. And then right here, boom, now that's the actual policy at work. Prompt. This is the request a human has given the robot. Palm Secan is constrained to commands that are safe for a robot to work. Can you bring me a drink and a snack to recover? The large language model interprets that into, I will bring a water bottle and an apple. So they have these additional concepts here. Affordance. What is affordance? The affordance model scores whether each step is possible for the robot and the environment. Okay, so some kind of value function, some kind of function being, of course, approximated by a neural network, likely, right? That takes the different parts of the human. Can you bring me a drink and a snack? So these are different steps. These are different actions that the robot could take. Find an apple, find an energy bar, find a water. And then you have a model here, the affordance model, that it's saying, okay, well, how likely is it that this action will result? Let's see the exact way that they say it here. Scores whether each step is possible for the robot in the environment. Okay, so the affordance model is just saying, is it even possible for me to find water? And then the LLM is the one that's actually saying, how relevant is finding water to this original command? And then the combined score, I guess, is the combined of those. So all the different possible things the robot could do, the one that is the most relevant to the user and the one that has and that is possible to execute, right? The affordance score, that combined score is going to be what the robot does. And you can see here how it's broken it down into kind of this step-by-step, this chain of thought. It's broken it down into find water, pick up the water, bring it to you, put down the water, find an apple, pick up apple, bring it to you, put down the apple. So for those of you that are a little bit more involved in robotics, you can understand how these are actually robot commands, right? Find a water. This is a localization task, right? So find this object, right? So that means move around in the world until you find this object or go to a specific place where that object is found. Pick up the water. This is grasping. So now you are there. You are there in front of the table. You can see the water. You know that it is possible to pick up. And now you just need to execute the actual manipulation task of going and grabbing that water. Bringing it to you. So now this is again similar to the finding task. It's moving around in the real world with the Roomba base. Putting down the water. This is a manipulation task. Another localization and kind of moving around. Picking up the apple, manipulation again, bringing it to you, localization again, putting down the apple, manipulation again, and then done. It's kind of alternating between movement and manipulation here. To turn off these fucking notifications from Slack. Cool, so that's a nice little blog post, but I also wanted to check out this one specifically here. Open world object manipulation using pre-trained vision language models. Abstract. For robots to follow instructions from people, they must be able to connect the rich semantic information in human vocabulary to their sensory observations and actions. Sensory observations, of course, they have the cameras in the head, but then they also have the laser sensor here. They also know the position of every single one of their joints. They also know the position of their base. And they probably already have a map of this environment, right? For sure, this robot has gone through this mini kitchen many, many times before, and it's mapped it out, so it largely knows where all the tables are and where the fridge is and so on. So it has a map of the environment. If you don't have that map of the environment, you are performing what's called SLAM, which is simultaneous localization and mapping, which is simultaneously figuring out where you are and simultaneously building a map of the environment. This brings up a notably difficult challenges. While robot learning approaches allow robots to learn many different behaviors from first-hand experience, it is impractical for robots to have first-hand experiences that span all of this semantic information. Yeah, so can you get me the pink stuffed whale? Like, how many times has the robot grabbed the pink stuffed whale? probably 0. So if we were in the old paradigm of having to explicitly describe every single step as part of a task, which is what people were doing 10 years ago, you would never be able to do that, right? Because what is a blue stuffed whale, pink stuffed whale, pink stuffed elephant, right? It's like there's kind of like an infinite amount of objects that you would need to grab. So the kind of fuzzy matching that you get from the large language model really makes that significantly easier. Right, it's never seen any data interacting with a stuffed whale before. Fortunately, static data on the internet has vast semantic information, and this information is captured in pre-trained vision language models. Vision language models are slightly different from language models. So a vision language model is something like CLIP, right? Or BLIP. BLIP is a image captioning model. CLIP is a contrastively trained language image pre-training, is actually what the CLIP stands for. But these are models that basically have been trained with captioned images from the internet, and they're very good at relating something in an image, right? Visual modalities with captions which represent what is in that image. So they can associate, for example here, fish with this particular part of the image that has a fish on it, right? And as far as the robot's concerned, it doesn't know that it's picking up a fish, right? At the end of the day, the manipulation task that it's doing is just, hey, this part here, this part of the point cloud, which I've segmented out with my vision language model, I want you to grab that with your little gripper, right? In this paper, we study whether we can interface robotic policies with these pre-trained models with the aim of allowing robots to complete instructions involving object categories that the robot has never seen firsthand. We develop a simple approach, which we call manipulation of open world objects, MOO. This is great. Very much approve of this, of this name. Open world, I guess there's no limit to the objects. Maybe that's what it means. Maybe it means that the map is open. Maybe it's not, the robot doesn't have a map of this world beforehand. Maybe it just means real world. I don't know. Which leverages a pre-trained vision language model to extract object identifying information from the language command and conditions the robot policy on the current image. So the robot policy, this is the neural net that actually the robot is running, right? So robots like this are trained with reinforcement learning. And reinforcement learning, you have the policy, which is basically the actual neural net that is producing actions, right? So it's the neural net that actually tells the robot how to move its hand, right? And you're conditioning that, which means that the same way that you would condition a diffusion model on text, you can condition a policy model on an image. And here they're conditioning it on the image, the instruction, and the extracted object information. So a couple different things going into that policy. In a variety of experiments on a real mobile manipulator. Mobile manipulator just means manipulator is the arm, right? And then a mobile manipulator refers to the fact that it's an arm on a base, right? Just a robot arm on a Roomba, basically. We find that MOO generalizes zero shot. So zero shot means that you're not doing any additional fine tuning for a specific task. It just works out of the box to a wide range of novel object categories and environments. In addition, we show how MOO generalizes to other non-language based input modalities to specify the object's interests, such as finger pointing. What? If that's real, that's fucking crazy. If you can just point at an object, and how it can be further extended. The policy is trained on demonstrations spanning a diverse set of 106 objects. Okay, so the actual gripping itself, so the policy that actually, the neural net that actually performs the gripping for the robot is trained on demonstrations, which means that at some point someone was sitting there in VR controlling this little robot, and they were sitting there grabbing 106 different objects. So that is what the robot manipulation is really trained on, is basically these humans that have been using that robot to grab it, right? Demonstrations, sometimes called behavior cloning in reinforcement learning. So the language model itself is not actually training the policy that grabs, right? It's not training the neural net that actually grabs it. The language model, or the vision language model in this case, all it's doing is it's just recognizing the part of the image that needs to be grabbed, and it's telling the robot, grab this part of the image. Grand milestone in robotics is to develop robots that can effectively perform various physical tasks for individuals in the real world. Yeah, I think that we're very, very close. You know, like, obviously people thought that was the case in 2013, and people thought that was the case in even 2000, right? Even if you go back and look at the Asimo robot that I think it was Toyota or Honda. Honda had an Asimo robot that was in the, like, what was it? Asimo Honda. Yeah, 2000. So in the year 2000, they actually unveiled this, and they thought that, hey, we're like a couple years away from these things coming in your house. And it turned out that they basically drastically underestimated the complexity of creating real-world robotics, and it's now 2023, and we don't have robots in our house. So maybe there's a little bit of hubris there, and maybe we shouldn't just assume that, hey, we can take this technology here and we can now have robots in the house, but we're getting very, very close, right? We now have robots that you can talk to in natural language, and you have videos of these robots. Look at this, demonstrations. Here's how it actually works, pick and place. Look at that. Although it does fail to pick up that fork there. You see it messes up a couple times. Pick the fork. So there seems to be 3 different ways. You can either basically point at the object, you can click on a specific part of the image, or you can describe it with natural language. Although current robotic systems have accomplished impressive feats, these systems are typically rigid and only function in a narrow range of behaviors. Often only those which they were specifically programmed or trained to perform. Robotic capabilities can be measured on 2 criteria, skills and objects. Skills refers to specific behaviors such as pick up X, move near Y, or take the lid off X, while objects refer to entities upon which the skills operate, such as pick up the apple, move the can near the soda dispenser, and take the lid off the coffee jar. This is kind of intense. Extending a limited set of skills to an unlimited set of new objects. Right, so the skills themselves are still limited. Each of these is still done the old-fashioned way where, or not the old-fashioned way, but the medium old-fashioned way, where you're basically using reinforcement learning to train a policy that does things such as grabbing or navigating to a specific location. Ability to execute manipulation skills on objects that were neither encountered during training nor explicitly programmed in the system in any way. In our work, we use the interface of natural language where the robot receives raw text and then executes the skill as described by the text command. Mu achieves state-of-the-art generalization for unseen object categories. I don't think there is a definition for state-of-the-art when it comes to manipulation. There's no benchmark that I am aware of, so this is a little bit of an overstatement, but this is probably, I do think that this is some of the most advanced kind of bleeding edge robotics there is, but there's no such thing as state-of-the-art. Our system employs an open vocabulary object detector, specifically OWL VIT. VIT here means a vision transformer. So this is a transformer that is specifically for vision, right? Transformers consume sequences of information, generally sequences of word tokens in a natural language context. But Vision Transformer, they basically take an image, cut it up into these little patches, and then treat those little patches as if they were word tokens, basically. To link natural language with objects in a visual image, given a command from a known skill, we break down the command into the skill and object components and provide the text descriptions to the object in order to obtain a bounding box indicator of where the objects reside in the RGB camera space. Okay, so at the end of the day, the output of this whole pipeline is just a bounding box. So you have the image, which is coming from the camera of the robot. You have the instruction, which is what the user said, right? Converted into text. You have your large language model. Where's the large language model? I guess it's down here. So you don't have an LLM just yet. I guess the LLM converted the original human command into this instruction. So this instruction is what comes out of the large language model. Move green sprite can near blue plate. This owl vision transformer, you see this little snowflake here? That means it's frozen. That means they're not fine-tuning that. They're not pushing any new gradients to it. It's basically the weights are frozen as is. It takes the image. It also takes what seems to be here, the blue plate and green sprite can, which are specific objects. It uses those and it gives you back these bounding boxes. These don't actually look like bounding boxes. These look like key points. I don't know why they say bounding box, but okay. You get the key points of each of those specific objects. Then the robot goes ahead and current image and recent history. So the fact that there's a bunch of these means that it's doing this on every step. So every step, the robot's motion is always split into steps. And even if you see a robot moving smoothly, it's still acting in a discretized time space, right? Film efficient net. What is film efficient net? Film efficient net, token learner, transformer, action. So this is the actual action that gets executed by the robot, right? And the robot has a bunch of different joints. It has, I guess mode probably refers to, am I picking something or am I moving somewhere? Right, so is it navigating or manipulating? That's probably what the mode means. The base is the base of the robot, right, the Roomba. So it probably has rotation and then X movement and then Y movement. So that's probably what the 3 numbers there mean. And then the arm is, right, a manipulator that has probably 7 degrees of freedom. So that's what each of these 7 numbers here mean. And these are all the different joints and all the different possible things that the robot can do. That's called the action space of the robot in reinforcement learning. We enhance the general purpose transformer architecture by incorporating the object locations in the form of a segmentation mask. Okay, what is going on here? Because here, this image very much looks like a key points, but here they're talking about bounding boxes, they're talking about segmentation masks, but I don't see a segmentation mask and I don't see a bounding box. I see key points. RT1 tends to be brittle when confronted with previously unseen objects because it has only seen data across a limited set of objects. Given previously unseen objects, RT1 will be confronted with a novel language embedding, making it difficult to generalize. Conversely, in Mu, the segmentation task representation is identical for both previously seen and novel unseen objects with simplified generalization. So RT1 is, I guess, the initial version of the system, learned via end-to-end, via behavior cloning from human demonstrations. So end-to-end here means that when you're designing these machine learning systems, right, which at this point are synonymous with deep learning systems, you can train them, you have different parts, right, and you can train these different parts separately, right? You could train the vision part separately from the language model part. You can train the control part separately from the vision part. But there's this idea that, hey, maybe you can just train the system end-to-end, like just end-to-end as in what is the human command, what is the image, and then what is the action, right? Go from the most input that you could have and then go to the most output that you could have, right? And that's called end-to-end. So end-to-end behavior cloning from human demonstrations means you have a human who's performing the task, and then you're saying, okay, the human saw this picture in the camera and moved the joystick in this way. So I'm going to train a machine learning system that, given that same picture, would move the joystick in the same way. That's what end-to-end is. We utilize OWL-VIT on the robot demonstration training data to generate genuine detections for conditioning the manipulation policy during the training loop. So the manipulation policy is the actual neural net that's actually choosing what to do in this action space, right? It's actually outputting individual actions to execute at every time step. And rather than the manipulation policy just being the result of end-to-end behavior cloning, right? The manipulation policy is going to be conditioned on the detections coming out of the VIT, right? So you're conditioning the policy on this output here, right? And that's not end-to-end anymore, right? Because this VIT is not trained on the robot at all, right? It's not been fine-tuned for the robot. It's frozen, right? The VIT model is just trying to say, hey, here's an image and here are some objects in the image. Here's where that object is inside the image, right? It has no specific fine-tuning in for robotics. Pick task, other task selected for scene valuation. What is this? Number of training episodes. So episode is basically one full sequence of a task, right? So for example, one episode could be the robot goes like this, and then it grabs the thing, and then it brings it here. And that's one episode, right? One episode could be the robot starts here, and then it moves, and then it ends, right? Like, so the episode is going to have a different definition for navigation tasks, manipulation tasks, but you could think of it largely as one chunk of data. So for these tasks here, blue plastic bottle, Coke can, Red Bull can, blah, 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 blue chip bag, there seems to be a lot of data, right? And they kind of show you here RT1 data. So maybe this is the data that they already had. And then they have these other here, newly added diverse pick data. So this is a bunch of new data. See how much broader. So initially the RT1 was very narrow, a bunch of very similar tasks, but a lot of data for each of those tasks. And now you have not a lot of data, but for a much larger array of tasks. And unseen eval here, what this refers to is that when you're training machine learning model, you want to evaluate on data that has not been used in training, right? If you evaluate on data that has been used in training, it's somewhat cheating, right? It's the same way that if you go, if you're in school and you take a physics test, the questions on the physics test aren't the exact questions that were on your worksheet or on your problem set, right? They're different. They're going to be similar, right? They're going to come from the same distribution of possible test question or possible questions, physics questions, but they're not going to be the exact same physics questions that you saw in your homework. They're going to be different, right? So the evaluation, right? These tasks, the bird ornament, the green cup, and the green Sprite can, those have never been seen before by the robot, which is why you can evaluate whether the robot is generalizing by seeing how it performs on these unseen objects. Our early attempts struggled to manipulate objects with shapes different from those in the training set. We hypothesized that we could learn most of the information needed to generalize skills to unseen objects by only incorporating more grasping demonstrations into the RT1 dataset. We added conditional grasping demonstrations across 90 diverse object categories as shown in the figure above. We found that we could transfer knowledge from these grasping or pick episodes into the existing RT1 skills. Okay. Here we have a little bit more information. You can see how beat up this little robot's hand is. You look at that. Look at how much like scuff marks there is on this little robot's hand. So this robot has hit its hand on a lot of things. It's probably like elbowed the table a million times. You have here a bunch of little objects and the robot's trying to pick these. Monocular RGB. RGB is a red, green, blue. It refers to basically a picture. Monocular means there's a single camera image. So here you have the actual camera image that the robot is looking at. I think there's multiple cameras in here, right? So I feel like you would get more if you used a stereo camera, right? I feel like monocular camera is a little bit lame. I feel like if you have access to multiple cameras, just use the multiple cameras, and you can probably get way better kind of performance. There's probably some implicit kind of depth that you could learn from that, right? Humans and pretty much every other animal in the world uses two eyeballs, right? Stereo, because you can kind of get an idea of how far away things are at the depth. But the dimensionality of the image they're using is 512 by 640, so 512 pixels by 640. 7 degree of freedom arm and 2-finger gripper. So 2 fingers, 7 degree of freedom refers to the fact that there's 7 joints on this arm, right? Randomized distractor objects. So you're going to put, if you wanted to maybe grab, I guess, this rolling pin here in this example, you're going to put other objects in there to kind of confuse it, right? Kind of a little bit adversarial, make it hard, kind of like the original Boston Dynamic video where they have it balancing and then they have that guy come and they kick it, right? And the point of the kick is to show you that with these kind of adversarial, in that case, forces, but in this case, weird distractor objects, the robot can still perform. A system's ability to generalize and perform skills on objects it has never encountered. To test this, we position our robot beside a tabletop surface that is covered with a variety of objects and then provide a natural language command to execute a specific skill. I mean, the skill is always just pick, so I don't know what that means. Other skills. What does other skill have to, like, what is another skill? Ah, okay, here you go. Move, open, pick, knock, pick, open, pick, move, place. So there's maybe a dozen different skills here. But they're all kind of variations of picking, right? Crush. I wonder if they have that. I wonder if they have a crush skill. We have established strong correlation between increased performance in larger dataset sizes and model capacity. This is the truth right here. If you do any kind of machine learning or AI, and you're like, wow, I just can't get the performance high enough, just make your data set bigger, make your model bigger, train for longer, and it'll probably improve your performance. Pretty much the entire deep learning world is this sentence right here. Increased performance because of large data set sizes and model capacity. You know that astronaut meme? Right? Like the meme is basically, wait, it was all just bigger data sets this whole time? And then the guy in the back is like, always has been, right? So don't listen too much to like the transformers is the reason that we're now doing this now, or oh, it was ConvNets is the reason that we got this. And it just comes down to the fact that the internet and digital cameras and cell phones and GPUs, like you have these kind of fundamental technologies at the bottom layer that are increasing the amount of data that you can train on, the amount or the size of the models that you can use, and everything else is just details, right? Really, the rising tide that is floating all the boats is the size of the data sets and the availability of increased compute and increased data. Demonstrated Mu is more robust than competing methods in managing distracting environments. We conduct extensive real-world evaluations of Mu performance on 13 seen objects and unseen objects. We ablate Mu's model capacity and training distribution. So ablation studies are where you take different parts of your system and you remove them to see which parts of the system contribute to most of the final performance. Here, ablating Mu's model capacity. All right, and we're back. So ablating model capacity here basically means they tried a couple different sizes of the model, and they will show us, I guess, down here which one performs the best. So I guess this is pick percentage. So compared to RT1, it performs significantly better. So you can see here RT1 picks, I guess, 54 out of 100. for seen objects and 25 out of 100 for unseen objects, and Mu 92 out of 100 and then 75 out of 100. So Mu does seem to be performing significantly better there.
What do you want me to pick up?
That's creepy. It's speaking.
The human is pointing at Torrent.
2x speed.
What do you want me to pick up? The human is pointing at Spoon.
So that's the large language model, the thing that's saying, what do you want me to pick up? And it's the human is pointing at. So the large language model is what's doing that, but the robot itself, or the policy, right? That's what's actually performing this little shitty grab here.
What do you want me to pick?
We explore using a generative vision language model like PALI to generate an image caption, which is then provided to OwlVIT to generate a mask usable by MOO. Generate an image caption. Okay, so you can upload an image. So if you upload an image, they'll use PALI, and I guess they could have used Blip, but it'll give you the caption. So here the caption will be something like red apple, and then that red apple will get interpreted by the OwlVIT model in such a way that you can condition the policy to pick that red apple. OwlVIT need not be conditioned on a textual query. It can also be prompted with an image query, such as a stock image. Image-based querying, little mistake here, is especially relevant when the objects are hard to describe in words, such as whether many visual solar objects in a scene. In these cases, it'd be most effective to directly provide an image of target of interest. So, querying, this is bothering me. Let's actually go to, here we go, dudes. This is how you get no mention of this. Let's go robot mu GitHub. Mu github.io right here. Nope. I want the actual GitHub to robot mu, not in this user, all of GitHub. And we don't want this, just robot mu. We want robot mu. Why did that open a new window? Robot mu IO. Here we go. Robot mu github.io, and we have the actual index. And we scroll down to this part here, image-based querying. So we can copy that, go into the here, we can Control F for that. And we can do this. We can edit. We can Control F. Control F, querying. Change this to querying typo. Propose changes. There you go. Fix that. We'll see if they do it. Great pull request. Typo. Relevant where objects are hard to describe, such that when there are many visual objects in the scene. Yeah, so if you tell it, hey, here's an apple, can I get more apples like this? And there's 4 apples. It's going to be hard, right? There's some uncertainty here with the OWL VIT, right? The OWL VIT is going to pick one of these 4, depending on which one is probably the most like a red apple, and it's a little bit uncertain. Okay. So here you scramble the object. So this is interesting. You see here how when you move the can over to the back, it stops doing the manipulation task, moves all the way around. So now it's a navigation task, and then does the manipulation task again. Pretty cool. Coincidentally, there is an open vocabulary object navigation algorithm called clip-on wheels. We implement a variant of clip-on wheels and combine it with moo, which we refer to as cow moo. Cool. So it's a little bit sad that the Everyday Robots has been shut down within Google, but I think the spirit of this research group continues, and I think that you're seeing kind of an explosion in robotics for sure, especially the humanoid form factor with Tesla. I think there's a couple other humanoid robotics startups nowadays too. And you can bet your ass that they're going to be doing this type of stuff, right? Using large language models to take human commands and basically convert them into a set of actions that the robot can execute. So I don't think this type of stuff is going to be, you're not going to have a robot in your house within the year, but maybe 5 years, and then definitely 10 years. I don't know, maybe I'm overstating that, but I feel like we have all the pieces now, and hardware has been getting better for a very long time, right? There's been companies that offer robots for decades and decades to things like car manufacturing and kind of these industrial applications, and they've been trying to figure out how to make motors cheaper, how to make these parts cheaper. Like the cell phone community has figured out how to make the cameras cheaper. The autonomous vehicle community has figured out how to make these little laser scanners cheaper. So like there's a lot of different parts of the robot technology stack that have just been getting better and better and better and better over time. And I think the kind of the kind of step function improvement that we've seen in language models and the way that they can understand natural language and turn it into a set of tasks, as they are showing here in this stuff, I may be optimistic, but I feel like that's a big missing piece that is now there. And maybe that's why you're seeing all these humanoid robots coming out, is because people are finally realizing that you can actually maybe do this. You can actually, within 5 years, have robots that can help you in your house. They can do the dishes for you. They can grab you things. They can clean up after your toddler and so on. So an exciting future where you can talk to your robot in natural language. Thanks for listening, and see you guys later.